Now that we've looked at law of large numbers, we're going to go ahead and take a look at probability. And that, thanks to the law of large numbers, we know that relative frequencies settle down. So that's why we call that the probabilities. That's what we're using. Now, probabilities must always be between 0 and 1. You know, it's not 110% that it's going to rain. So a probability of 0 indicates impossibility, and a probability of 1 indicates certainty. Sometimes we're interested in combination of outcomes, and we call that, that could be an event. So we have a die is rolled and comes up even. So when thinking about what happens, things are simpler if they're independent. What does that mean? That means the outcome of one trial doesn't affect the outcome of the other. For example, flipping a coin, the coin does not know what you flipped last time. So it's not going to influence saying, oh, I've been doing heads, I better switch to tails, okay? And that's why coin flips are independent. In everyday speech, we do use probability a lot. But when we do it and we're just kind of saying this or that, we're being very subjective or using personal probabilities. So we're going to stick with more formal probabilities. We're not going to be using personal probabilities because those don't have the consistency we need for these rules. Okay, so there are two requirements for probability. It's a number between 0 and 1, just like I said before. It can be all the way down to 0. It can be all the way up to 1. But it has to be somewhere in that range, okay? And then we have the something has to happen rule. In other words, I need some outcomes. And when I do the probability of all those outcomes put together, it must be 1. So I'm going to give you an example, and we'll talk about the outcomes. And we'll go ahead and calculate a probability. So I've got a traffic signal to cross A.W. Grimes at Gattis School Road. You've seen it. It has a timing sequence of 20 seconds of green, 62 seconds of red, and 3 seconds of yellow. What is the probability that the light will be red when you get to the intersection? Now you're probably going to say, person, it's 100%. It's always red when I get there. That's your personal probability. Let's go ahead and calculate what the actual probability would be. So first of all, we got to list the outcomes. We've got green for 20 seconds, red for 62, and yellow for 3. Maybe it's easier to think of this as you have 20 green seconds, 62 red seconds, and 3 yellow seconds. So that kind of gives us our frequency table. And our total number of seconds is 85. So the probability of being red is the number of outcomes for red, and we're saying there's 62 red seconds, and there are 85 total seconds in the sequence. So we calculate a probability of 0.729 or 72.9%, which you're probably going, yeah, that's not 100%, but it's kind of close to what I'm running into, okay? So now there's the complement rule, which says the probability of something not happening, so the probability of not getting a red, would be the rest, right? It would be getting a yellow or a green. So the probability of an event occurring is 1 minus the probability it doesn't occur. So we're going to go ahead and take our example we just did, and we know the probability we just calculated is 0.729 or 72.9%. I don't have to do another fraction. I can just say the probability of the complement of a red light, in other words, not red, is 1 minus the probability of a red light, which would give me 0.271 or 27.1%. So if I already know the probability of something, find the probability of not that something is just subtracting from 1, and it's pretty darn easy. Now, we can also use the addition rule so that as long as you have events that have no outcomes in common, in other words, they're disjoint, they're exclusive, we don't have a probability, you don't go up and you see the light being red and green at the same time, or red and yellow at the same time, or green and yellow at the same time. Those are disjoint. They don't happen at the same time. They're mutually exclusive. So for two disjoint events, the probability that one or the other occurs is you just add them. So I could go ahead and calculate that the probability will be green or yellow. So I've got 20 green seconds and 3 yellow seconds. Well, I could calculate the probability of each one. Probability of green is 0.235. Probability of yellow is about 0.035. When I add it, I get 0.270 or 27%. Now, some of you sharp kiddos are going, wait a second, you did not red and you got 27.1%, which would be the same as green or yellow. That's just a rounding issue. If I actually do 23 over 85, I do get the 0.271. So that's kind of a lesson there. If you're trying to be kind of exact, it's actually better to add it before you do the divisions, because up here we're being forced to round early. Here we don't round to the end. Rounding to the end is always preferred. So let's go ahead and take a look at the fifth rule, which is the multiplication rule. So if there are two independent events, A and B, the probability that both A and B occur is a product of the probability. So I could say, Monday, what's the probability of getting a red? And what's the probability of you getting a red light on Tuesday? So you would just take that 0.729 times 0.729. Or you could say probability of getting a red on Monday, but not a red on Tuesday. You go to the 0.729 times the 0.271. I'm going to give you a different example here. We have batting averages. This is from 2015 or 14 for some of the Round Rock Express players. Carlos Peguero had a 0.667. And there's a bunch of others. I'm going to use Carlos Peguero and Tomas Telis. So this one's a great example because we're going to find the probability that Carlos gets a hit. So they're going up to hit. The first two batters for the third inning are Carlos Peguero and Tomas Telis. I'm going to calculate a probability that Carlos gets a hit, and Tomas isn't so good at the hitting, so I'm going to calculate the probability that he doesn't get a hit. Okay? So what I'm going to do, you see the symbol notation. This also means and, by the way. The probability of Carlos getting a hit is 0.667. The probability of Tomas Telis getting a hit is 0.33, but I want the probability he doesn't get a hit. So I have to subtract that from 1. So I end up with 0.667 times 0.67. 1 minus 0.33 is 0.67. When I multiply both those together, there's about a 45% probability that this is going to happen, that Carlos is going to get a hit and Tomas does not. Here's another example. What is the probability of rolling a number greater than 4 on a 6-sided die and drawing a jack from a deck of cards? By the way, you should get familiar with die and cards. So here we have the probability, and I just said greater than 4. That's my notation for it. And getting a jack. Well, since the cards and the dice aren't mixed together, they're disjoint, they're exclusive, right? And so I can go ahead and use the multiplication rule. Well, the probability of getting greater than a 4 on a die, there's 5 and a 6 out of 6. So it would be 5 and 6 are 2 outcomes out of 6. So that probability is going to be 2 out of 6. And for a deck of cards, there are 4 jacks and 52 cards. Please memorize that because that might show up. They expect you to know about cards. Okay, so you just multiply those two together, and here I got a fraction, 1 out of 39. So one thing is, on the multiplication rule, is that the independent events A and B have to be disjoint. If they're not disjoint, if they actually overlap, this multiplication rule doesn't work. So you need to always think about and make sure that they are independent. Don't just assume they're independent. Always think about whether it's reasonable to use this rule. Last thing, a notation alert. Well, almost last thing. Notation alert. In this text, you can see probability of A or B with words and probability of A and B in words. You will also see this, which means union. So that's the or. And when it's curved opening down, that's the intersection, also known as and. So be prepared to see these two different notations in work and outside of the book. Okay. So what can go wrong? Beware of probabilities that don't add up to 1. Don't add probabilities of events if they are not disjoint. And we'll go over some more of those in the next chapter. And don't multiply probabilities of events if they're not independent. Don't confuse disjoint and independent. Disjoint events cannot be dependent. All right, and I have the feeling we'll go a little bit over that more in the next chapter.